Let's take a look at translation options and the stack decoding algorithm for phrase-based statistical machine translation. We're going to be working with a variant of the example given in the Chapter 6 slides associated with the Statistical Machine Translation textbook by Philip Kern. Here's the example sentence. If you want to follow along on the slides, these are going to be the Chapter 6 decoding slides at statmt.org/book. Okay, let's start with a simplified version of the example sentence shown there. This is a German sentence. Er geht nach Hause. Okay, so Chapter 6 slides, if you look at slide number 9, you see a whole bunch of translation options. For the purposes of this example, we're going to simplify this quite a bit and assume that there are only a couple of ways to translate each word and a couple of ways of translating one or two of the phrases. So let's organize. So for every one of these words, we're going to assume that there's a couple of ways to translate it. So for example, er could translate as he. Er could translate as it. We will draw a box, a couple of boxes over here to indicate that he and it are both ways of translating er. Let's also take a look at gate. So let's say that gate could be translated as go or as goes. All right. Let's assume that nach can be translated as after, and Hause could be translated as house. And let's further assume that nach Hause, taken together, could be translated as home. This is a very simplified example, as there are other ways of translating these items, but for simplicity, we're going to stick with this. Okay, so where do we go with the stack decoding algorithm? Well, we're going to start off by assuming that we haven't translated anything at all. We're going to organize our translation by the number of words that we have translated so far. So at this point, we have translated 0 words. And I'm going to mark that by drawing a box that contains 0 words in it. More importantly, I'm going to delineate this top section of the box, this part, with 4 squares. Here, 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 and here. The fact that they are empty indicates that the first word has not been translated, the second word has not been translated, the third word has not been translated, and the fourth word has not been translated. For the purposes of this example, we're going to assume monotone decoding. That means that we can only translate the next word in the sentence. So at the beginning, we're going to start by translating er, and then gate, and then nach, and then Hause, although we could translate nach Hause together. In a real machine translation system, reordering might be allowed, in which case you could, for example, start by translating gate. So you would start off with go in that example. However, we're not going to allow this in this example. Okay, so we're going to do monotone decoding. The other thing that we're going to do here is hypothesis recombination. Okay? Hypothesis recombination is going to allow us to draw a simpler graph structure than would otherwise be allowed. When we're talking about hypothesis recombination, it's very important to specify the Engram language model order. In this example, we're going to assume a bigram language model. In other words, the n in the Engram language model is going to have a value of 2. That means that at any given point, the language model is going to ask, what is the probability of the word at the current time step, t, given the one previous word, t minus 1? This is an instance of the Markov assumption. The Markov assumption states that only the n minus 1 words of the history matter with respect to the model. Words farther back in the history are going to be assumed to not be relevant. Okay, so let's get started with our monotone translation. Recall that monotone just means no reordering. Okay, so let's start by finding all of the possible ways that we could translate er. Well, we could translate er as he, or alternatively, we could translate it as it. Let's do both. So the stack decoding algorithm says start with the current stack that you're on and extend it every possible way that you can. Once you've done that, move on to the next stack. Extend every item in that stack every possible way that it can be extended. It's possible that you can jump ahead so that, in principle, an extension from stack 1 could go all the way to stack 3. Remember, stack numbers just tell us the number of words that have been translated so far. So in stack 0, 0 boxes have been filled in. In stack 1, 1 box will have been filled in. By the time we get to stack 3, 3 boxes will have been filled in. Okay, so we're starting at the beginning and we're going to extend the empty hypothesis using all of the possible ways of translating the first word, er. Er could be translated as he. Now, when we create this extension, it's going to go in stack 1. Why? Because exactly 1 word has been translated so far. We're now going to extend the entry in stack 0 a different way. How? Well, er could also be translated as it. Again, exactly 1 word has been translated so far. Now, I said that we're doing monotone translation. If we were doing translation allowing reordering, then we would also have other extensions involving one word, such as this, where gate could be translated as go. That's allowed if we are allowing reordering. It's not allowed if we're doing a monotone translation. Note that if we were allowing reordering, this newly created hypothesis would go in stack 1 because exactly one word has been translated. One of these 4 squares has been filled in. Doesn't matter which of them in terms of the stack placement, just matters how many. But since we're making an assumption of monotone translation, let's get rid of this to simplify the graph. Okay. Next, we're going to extend he and extend it. Let's extend he by translating gate as goes. Okay. Because we extended he, the box from he already has to be filled in. Because we just translated the second word in the source sentence, we have to fill in the second box. Because 2 boxes have been filled in, we are in stack 2. Okay. Now, we also could have extended it by translating gate as goes. Okay. We also could extend he by translating gate as go. We also could have extended the translation of it by translating gate as go. So, 4 possible ways of getting to this point in stack 2. All right. Now, let's think about hypothesis recombination. When it comes time to extend go, we could extend it by translating nach as after. So let's look at what the language model has to say about that. The language model is asking, what is the probability of after given go? Let's hold on to that for a moment. And let's extend this cell after. Sorry, forgot to fill this in. Okay. What's the language model have to say about this point? Well, it is also going to ask, what is the probability of after given go? What is the probability of after given go? All right, what about down here? Well, we could extend goes by translating nach as after. What's the language model have to say about that? Well, it is asking the probability of after given go, or rather goes. Probability of after given goes. What about down here? what is the probability of after given goes. Now, there's something that we should see that's held in common. Those two language model queries are asking the same thing. These two language model queries are asking the same thing. This should raise some alarms in a good way. When we extend go by putting anything here, the language model history is going to be the same as in this situation. So regardless of what we put here, this part, the language model history, is going to be the same. Likewise, down here, the language model history is going to be the same. Goes, goes. So, that means that when we extend this hypothesis cell, this entry, with something over here, regardless of what that something is, we're going to end up that these two are the same because these two had the same language model history. Because of that, there's no reason to have the duplication that we see here. Instead, we can get rid of this and instead have he and it point to the same go. Exactly the same thing can happen down here. These are going to be equivalent from the perspective of the language model history. Therefore, we can get rid of the duplication and have he and it point to the same space. Okay? Let's clean this up a little bit. Okay. Now, we can move on. So far we've got four possible translations. We've got it, go, we've got it goes, we've got he go, and we've got he goes. Let's extend it. So let's extend go with after. 3 words have been translated, therefore this goes in stack 3. Let's extend goes by translating nach as after. Now, we notice here that when we extend either of these, the language model history at this point is after. Probability of something, which I'm just leaving as a question mark here, given after. For here, the language model query is here, and that same language model query is taking place here. That tells us that from the perspective of the bigram language model, applied at this point, the history is indistinguishable. Therefore, we can collapse these two nodes through hypothesis recombination. Okay? Now there's 2 more ways that we could do extensions. One, we could translate Hause as house, extending this hypothesis here. How many words have been translated so far? Well, at this point, we already had 3 translated. And we have now translated the 4th word as house. Therefore, we fill this in. We've got 4 boxes filled in. 1, 2, 3, 4. Therefore, we are in stack 4. We now have the following possible translations. It goes after house. It go after house. He go after house. And he goes after house. But there's one more possibility. Home. We could translate nach Hause as home. What would that look like? Well, we could extend go. Why could we extend go? Well, go has the first 2 words translated, but the last 2 words haven't been translated yet. The last 2 words are, in fact, nach Hause. We could similarly extend goes by translating nach Hause as home. What we could not do is extend this spot, this node. Why not? Because we've already translated the first 3 words and we only have the last word to extend. Notice here, the 3rd word has already been translated. Translating nach Hause requires us to translate the 3rd and 4th word of the source sentence, but here the 3rd word had already been translated as after. We can't translate the same source word twice, therefore we cannot extend this by translating nach Hause. But we can extend this, and we can extend this. Okay, so where would that go? Can't go here because that would, once we've extended this by translating nach Hause as home, we see that we have 4 squares filled in. But stack 3 mandates that only 3 squares have been filled in. So this has to come over here and live in stack 4. Okay. Now we have the same issue going on again. We could extend goes with home. Now remember what we did before. We could write this up here, fill it in, do the extension, but we're going to notice right away that we've got hypothesis recombination is a possibility here. And so I'm not even going to bother writing that. We're just going to connect goes to home. And this constitutes the entirety of the chart parsing algorithm, or excuse me, not the chart parsing algorithm, the stack decoding algorithm for this sentence. And this represents the search space of possible translations of our original source sentence given a set of translation options, given a reordering limit. Here, the reordering limit is zero, meaning we're mandating monotone translations. And we also have to specify an Engram language model order here of 2. This was also critically important because we can't know whether hypothesis recombination is allowed without knowing the Engram language model order, because the Engram language order -1, it tells us how far back in history we need to look when attempting hypothesis recombination. So that's it, a complete working example of going through from a source sentence, examining the translation options in the context of a specific reordering limit and in the context of a specific Engram language model order. Had the language model order been different, for example, had we done language model order 3 instead of 2, then several instances here of hypothesis recombination would not have been allowed. So, for example, we could not have done hypothesis recombination here with language model order 3 because the history at this point would be it go, which is not the same as he go. It go and he go are different. Therefore, this node would have had to have been 2 separate nodes. One coming from he and one coming from go. Or, excuse me, one coming from he and one coming from it. Sorry. All right, that's it. Thank you.